everything that we are working through in here. So if you have 9-2 down, that's a good thing because we got some stuff. What about the review parts, 5-1 and 5-2? Those had the laws of exponents in there. And so those were important too. So any questions with those? What we have to do? Because 9-3 is all those logs, or not logs, all of the rules that go along with the rules of exponents. That's why we put that in there. Yes? You have an example? But what ones was it? One of the division ones that has the 2 pieces? Okay, I can find some of those. So the division ones from 9-2 that had a combination of things like this one, I think. Like that? Is that what you're thinking? No? From 5.2. 5.2. That was the 9.2. Okay. 5.2. Let me find 5.2 in my book. That will give us some examples. Something like this one. We'll try this one. 4x squared, 4x to the negative 2, 6x to the 5th, all over 9y, and 2y to the negative 1st. Something like that? Or am I still off? I'm still off. Not this one. No? I guess you gotta. What one? Is there any there that look like it?
No. It's really weird how they have made it.
Or was it 5-1?
It's 5-2. This one right here.
Oh, that's a written scientific notation. Okay.
Yeah.
Yep, those are over here. So it's scientific notation. So it's like these. Like these. Write them in scientific notation.
Yeah, but it's the division one. I don't understand.
Like that one?
Kind of like that, yeah.
Like this one or that one? Like
Yeah,
those?
like one of those.
Okay. All right. Well, at least we know what we're putting up here. Okay. So scientific notation. And we're looking at one that looks like this. 0.005 times 650 times 3.3 all over 0.0011 times 2500. Now your calculator will handle this. In Hawks it says turn on scientific notation, but your calculator will handle that. So if you take this whole top part, put on your calculator. Okay? So if we did that and not turn it into scientific notation, we can end up getting that for our value. So 0.005 times 650 times 3.3, and that gives me 10.725. Then if I do my bottom, 0.0011 times 2500, that gives me 2.75. Now all I need to do is to do my division. So 10.725 divided by 2.75, and I get my answer of 3.9. Does that help you? Yes or no? Pardon? Not really? Okay. If you turned it in scientific notation, then you'd have to move those back 3 places and get 5 times 10 to the negative third times 6.5 times 10 to the second times 3.3 times 10 to the 0, because I didn't move it anywhere, all over 1.1 times 10 to the negative third times 2.5 times 10 to the third. And so if you do this part out, then you still got to multiply all your numbers together. Then add your exponents. So negative 3 and 2 gives me 10 to the negative first. And 5 times 6.5 times 3.3 equals 107.25. But that needs to be converted because this needs to move back 2 more spaces. So I get 10 or 1.0725 times 10 to the negative third. Bottom 1.1 times 2.5, and that equals 2.75. And these cancel each other out. So then you just stick that on your calculator. Is that what you're asking for? I guess I don't know. Or were you just asking about turning? That's like that. It's similar. Let me get a piece of paper and put that one on there. Was 0.033 39 times 0.0044 all over 0.22 times 0.013. Okay, still like it. I mean, the only difference with this one is this one didn't have as many decimals in it. The one that you're looking at is this one. And so if we look at this one, what in the world we got going on? So again, use your calculator. Just multiply this stuff out. So 0.039 times 0.0044 and get that answer, 2.749824. And then do the bottom, 0.22 times 0.013, and we get 0.00286, and then take these and divide them. Pardon? Oh, we're getting there. So then I got to take 2.749824. Now make sure I wrote it down. Put it in here, right? 2749824 divided by 0.00286. And then this becomes my answer. So my answer is 961.478. But they might say, does that have to be in scientific notation? Does it say? Did I have mine in here wrong? Oh, I had an answer in front of it. 0.039 times 0.0044. That's why I had my answer in front of that. So that comes out as an answer, okay? Is that what you have? Okay. I didn't have the answer part in front of it. 1.716 times 10, that little e, that e in there, means that's times 10, and this negative 4 is your exponent. Okay? then that's all over 0.00286. So that divided by 0.00286, and I get 0.06, or 0.06, or 600ths would be my answer to that one. Sorry about having that answer piece in front of that one, because that's what messed it up. Okay, that makes sense, hopefully, because it's just putting it on your calculator. And it's just going through. Now you can connect them if you put parentheses around the top part, divided by parentheses around the bottom, and hit enter, and it'll do it all as one. So it just depends on what you've got going. Anything else in Chapter 5's reviews with any of those? Are we good, do you think? Okay. All right. So let's take a little second here and review those properties that were in this section. And my properties, the first one is if I had things that multiply together, what did you do to the exponents? If the bases were the same, and I had those raised to an exponent, what did I do to those? What happened to the exponents? Nobody knows? What did I do if the bases were the same? Pardon? What did you do to them? You add them together. 3 plus 4 is x to the 7th. So I add my exponents. If my bases match, I add my exponents. Another one is if I had x to the 4th over x to the 5th. What did I have to do then? Because if I am taking these things and I am dividing now, what do I do with my exponents? Cross them out? Is that what you said?
Yeah, like you would just, yeah, on the bottom.
Okay, so basically what I'm doing is I'm taking my exponents and subtracting them and ending x to the negative first, but we also had a rule about negative exponents that they can't be in the top. They need to go to the bottom and become positive because they move, okay? So we had that one. Another one is if you had x to the 5th raised to the 4th on the outside, what happened then? What did I do to those? Exactly, yep, times it by, these multiply each other, so I end up with x to the 20th, or I would have x and 5 times 4 and get my 20th out there, or my 20 power out there that I would have. If you had x to the 0 power, what's it equal to? Nope, not equal to 0, it's equal to 1. Yep. Any value raised to the 0 power is equal to 1 outside of 0 raised to the 0 power. It doesn't have any meaning at that point. Let's see, what else do we have in there? For the basic rules, they had, if we had a negative exponent, remember they went to the bottom. If the negative exponent was in the bottom, it went to the top. And so we would move it and switch and adjust our different pieces in there. These laws of exponents, if you want them all in one particular spot, if you take a look in your front cover of your textbook, they are there. They are listed as all of the exponent laws that are listed right here in the front cover of your book. So if you need them, they're there. And then they're also at the tail end of Chapter 5, there is, all of those are listed in the review section back there. So make sure you have those and that you know what they are, because when we get into today's stuff, we're going to work with fractions with these. So today's involving these same rules. Oh, one other one that we should have in here is if I had a squared b to the 4th raised to the 5th, I would distribute and give a 5 to everybody. And because it's distribution, it becomes a multiplication. So I end up with a to the 10th and b to the 20th. So that distribution part happens in there too. So we want to make sure that those rules are right there and are present when you work with them, so that you know what those are going to be. because as soon as I mention fractions, that kind of throws things in there too, because now we got to have all our fraction rules. That means if I have different denominators, I need common denominators, and adding those things together, multiplying fractions, moving fractions from denominators, and so forth. So just keep that in mind, that you got all these properties and rules that apply to that. So 9.3, if we get started on that section. In 9.3, I get my thing back around here so it's nice and semi-straight. If I can get it there. So in 9.3, we're going to look at rational exponents. And rational exponents, again, are fractions, or fractional exponents. And we worked with rationals back in chapter 7. These, of course, are not as hectic as those happen to be. So first, we're going to understand what's meant by the nth root, translate the expression to radicals. We're going to simplify the expression using the properties, and then we're going to evaluate expressions in the form of m over n with a calculator. So you're going to have to use your calculators again today so that we have that in place too. Okay, so what's meant by this? So if we look at nth roots, in your radical from on last week, we talked about indexes in here. Some have indexes if they are 3, 4th, 5th, 6th roots. If it's a square root, we know that there's no number here, but it signifies to be a 2. Okay, so we know there's a 2 there. So if I take these and I write them into a fractional form, it's going to be 1 over whatever that index happens to be. So the index ends up becoming your denominator in your fraction, is what we have happening. So if n's a positive integer, then we have a to the nth, or the nth root of a, or we have a to the 1/nth, assuming that n's a real number. So it's called a radical when it's in that form. The radical symbol is what we have here. The index we talked about, that's the n part. The a is the radicand, that's the number that's underneath your symbol. We talked about those the other day, so I know those aren't anything brand new. So if there's no index, it's understood to be a 2. So you want to make sure you have a 2, such as if I had the square root of 3, there's a little 2 here, or I write that in the fractional form or radical form by putting it as 3 to the 1 over 2. So it's turned it into a fraction at that point. So continuing on with this, so again, we get that expression. But a needs to be non-negative, and we don't ever have negative indexes with what we're going to deal with. So you don't have to worry about that part. So they're all going to be positive. And so, so when a is negative, the n must be an odd number. And we talked about that last time too, because when we had something like the square root of a negative 49, we said that was a non-real number. And we couldn't do anything with it because I cannot take a square root of any negatives. It will not work. But if it were the cube root of a negative 81, that's fair game, okay, because of that negative that's connected with it. And we learned last time we can pull the negative out and just simply look at the cube root of 81, because if I take a negative 1 and a negative 1 times a negative 1 times a negative 1 is still a negative. So I can just pull it out of there and work with it that way. So I can still have negative bases as long as this is odd. So just making sure that that piece is in place. So if we take a look at some of these and we reverse them and take a look at what in the world is it asking me to do. Well, if you remember, the 2 that's in the bottom is the index. The 1 up in here is going to be an exponent once we get to that stage. So what is this really? Well, if I take it and reverse it, the 2 is my index, the 49, which is the base, is the radicand, so this is the radicand. It can go underneath that, so what's the square root of 49? And we did that last time. So the square root of 49 is a big whopping what? 7. Perfect. Yep. And here, the 4th root of 81. So 4 is my index. 81 goes underneath. And if you can't look at that, last time we broke 81 apart. So 81 became 9 times 9. And 9s became 3s. So really, I have the 4th root of 3 to the 4th power, or simply 3. We good there? Okay. This one, 30 is my index. Negative 8 is underneath. So the 3rd root of 8, if I break 8 apart, 8 is 2 times 4, and 4 is 2 times 2. Or I have the negative 3rd root of 8, which is really a negative 2 when I'm finished with it. Okay or not okay? Right. This one, we might want to use our calculators to do that. And we can put exponents that are not a whole value of exponents still by using our caret key. But we need to do some stuff of putting some things into parentheses when we do that. So if we put this on our calculator, we can put our base in, which is 0.000, let's see, 4 zeros and a 1. Hit your caret key. But instead of just hitting the caret key, we're going to put this inside of parentheses. And we're going to go parentheses 1 divided by 5, parentheses. And then what I can do is, if you got the newer calculators, you got to hit that over arrow key to put it back down. And now if I hit enter, it will give me my answer, which is 0.1. So we can use our calculators to help us with this stuff too. Some of these are exact. If they're not exact, then you can go back to what we did in 9-2. So some will work out, some don't end up working out. So if I did this one, 2 is my index of a negative 16, but what do I know about that? So the square root of a negative 16 is what? What would I say about it? I'd say it's non-real. So we can't do anything with it. So it stays in that format. Okay? So first off, that's kind of the first basis here of going through and getting that stuff solved and figuring out what we have. Okay? So those pieces all end up coming together. So it's what we have. Okay. So any questions with this so far? Again, the denominator in every one of these is your index, and then your base becomes your radicand that goes underneath your radical symbol, and you end up solving them from there and having them turn into what they happen to be. So now, a summary of the rules of exponents. We kind of went through that earlier. I'll leave this up for a minute if somebody at home is watching these so that you have those. But we kind of reviewed all of them. Exponent of 1 just stays as a base. 0 came out to be 1. We multiplied and you added. We divided and we came up with a difference between those two. A negative exponent moved to the bottom and became positive. A negative exponent at the bottom moves to the top and becomes positive. The distribution piece, distribution here, and this one I didn't have in there, but you distribute the n by each piece within your fractional part too. And so you come up with those. And so we're going to take these rules and we're going to work with some other stuff. If you look at the very top up here, rational exponents in the form of m over n. If you look at this, n is still the index. M, we've added now, and m is an exponent that's on whatever your base happens to be. And so we end up coming up with these type of a situation. And if you always remember that m is the exponent, n is the index, you should be good. All of these, this whole piece, a underneath the radical, n is your index, m that's the top or the numerator is going to be your exponent that's on this, then you'll have your pieces together. It can look either way. Usually, this one is easier to work with than this one, because this one your numbers get huge. This one you might be able to find whatever root it is of a and then just raise it to a power. But if you raise it to a power first, then get your root, you get pretty big numbers out of that one. So let's see if we can reverse some of these and put them back into radical form and see what we can come up with. So again, x is always inside of your radical sign. The 3, the denominator, is always your index. The 2 is always your exponent. So really, I have the cube root of x squared. But again, I don't have any idea what x happens to be, so then therefore I can't work that part out. So x is just x at this point. If we could throw a number in there, then we could end up solving it. So what about this thing? Well, in this case, the 4/5 only pertains to the x, not this 3. So the 3 is going to sit outside. We're going to have a radical sign. X is my base. 5, what's 5? 5 is always the index. And 4 is my power that's on here. Okay, this one, we're going to leave the -1 out inside. Now, if this would have been inside of parentheses, if I would have had parentheses, if it would have looked like this, -a to the 3/2 with parentheses around it, that negative's connected to the a. But if it's not with parentheses around it, then you don't have that combination in there. So where does it go? So -a, no negative in front of here, it's just a. A is my base, that's my my radicand. 2 is my index, and 3 is my exponent outside. If it were inside of parentheses, then it would have been a -a square root of 2 index, or value of 3 on the opposite side. So this one, we can end up actually pulling an a out of here because it's a cubed, so I can pull out an a. So I have a -a, the square root of a, if I broke it down and solved it all the way. This one, can I do anything with this? Can't do anything with it, right? Because my base is negative, and so this one would always be a non-real. Until 9.7, when we have a way of dealing with those, but not today. So that one's just going to be what we happen to have there, okay? Questions with this of reversing them. Always the base is your radicand, the denominator is your index, the 2 is your exponent in this case on those. So let's see what happens if we reverse them. Now we want to take them and we want to put them back into fractional form. And so we've been taking and we've been saying, okay, what are our pieces in here? Well, the a, which now is my radicand, is going to become my base. My 6, which is my index, is my denominator. The 5 is my exponent, and that becomes the numerator of my fraction. So they go back and forth here between those. So what about this one? We've got a 5 out in front, so that's not affected. We have an x. It has no exponent, so there's a 1. No index out in front, so if there's no index, that means it's going to be a 2. So that's what it becomes. Okay. So then this one, going to have the negative out in front. 4 is my base. no exponent, so it's 1. 3 is my denominator. So we flipped them around and made them into other values. Are we good there? Need some more of those? What do you think? Again, index, not index, but the radicand is your base. The index becomes your denominator. The exponent becomes your numerator. So here, base, index is 2, denominator, and 1 because there's no exponent on there. But I need a 1 to create my fraction with those. Yes? No? What do you think? Okay. Let's take a look at some combining of these things now. Now that we know what we've got happening with them, now we start getting into using our laws of exponents. And the laws of exponents, in here, I need to look at what those laws were. We reviewed those. That's why you did 5.1 and 5.2, so that we could review these laws in here. These are my bases. They match each other. So what would I have to do with my exponents? So what I would do with my exponents is, because the bases are the same and I'm multiplying, I'm going to add these things together. So if I'm adding them, I need a common denominator. So what would my common denominator be? Of course, it's 6. Way back when we reviewed those, when we did stuff in chapter 7. 3 goes into 6 twice. 2 times 2 is 4. 6 goes into 6 once. 1 times 1 is 1. So 4 plus 1 is 5 6. So my answer is x to the 5 6. Does that make sense? Okay. So again, it's just dealing with those exponent laws and the exponent pieces that we happen to have in there for those. This one, a division. So what happened when we divided exponents? We subtracted them. So I need to take 3/4, take away 1/3 from it. Again, common denominator of 12. 3 goes into 12, 4. 4 times 1 is 4. 4 goes into 12, 3. 3 times 3 is 9. 9 take away 4 is 5/12. So my answer is x to the 5/12. Now, if it said turn this into rational form, then, or radical form, then I would have to say I'd have x to the 12th power, but x is to the 5th underneath. So that would be reversing it. Not that it's going to ask you to do that. It'll probably ask you to leave it like this, okay, within that. So it's not going to change that piece and let you know what is happening with it. Here's some other ones. My third got cut off here for some reason. So what would happen with this one? I have 2a to the 1/4. So it meets the laws of distribution in here. So we get 2 to the 3rd power. And then 3 times 1 is a to the 3/4. 2 to the 3rd needs to be worked out. So 2 times 2 times 2 is 8. A to the 3/4. So it's kind of the manipulation of what we got going with those. Okay. So what does this one do for us over here? So 27 to the 1/3. Why? 1/3, if you take 9/10 and times it by 1/3 on the side over here, the 3 and the 9 cancel. So I'm left with 3/10. But 27 to the 1/3 is really 27, or the cube root of 27. So the cube root of 27 is really 3. So I have to take it one more step so that I end up breaking it apart and getting it down to its final value. And again, because 27 is 3 cubed, so I can pull out a 3 out of that one. What about these guys? You think they're all right too? It's that distribution that you need to make in there. So you want to watch that and make sure you get your distributions done. And this one, what could we say about this piece? This piece is kind of a strange thing here. I've got a negative half, but I have a negative base. So what could we really say about that whole thing? My base is negative. So this tells me I'm going to move it to the denominator. Because of the negative exponent. But if I reverse this, square root of a negative 36, we end up with one of those non-real values. So I can't really work it out, okay, because of the negative in there with that negative 36. How about this one? 9 to the 2/4. If you look at 2/4, what do you notice about it? 2/4 can be reduced, right, to a half. So really, I have 9 to the 1/2. Turn it back into radical form. Index is 2. Base is 9. Raise to the first power. What's the square root of 9? And we probably all know that one. Ends up being a 3. Okay, so it ends up being a 3. The manipulation of these is, I think, tougher than probably what math you happen to have in them. And let's take a look at this guy. And let's see, this one's kind of got everything tossed into it, just like they did in 5-2. So we've got inside of here, you may want to get rid of all your negatives first. So 49 is positive, it stays. X to the 6 stays. Y to the negative second, where does it go? Does it move or does it stay? So anytime I've got a negative exponent, it's going to go to the bottom. So z to the negative 4th is going to come up to the top. Then do your 1/2 of everything. So distribution, everybody, including the 49, gets a half. So 49 to the 1/2. X to the 6 times 1/2. So 6 over 1 times 1/2 is really plain old 3. Z to the 4th times 1/2 is really 2. Finally, 2 times 1/2 is really 1, so I get plain old y. But then I need to take the half of the 49. So what is the square root of 49? So square root of 49 is 7. X to the 3rd, z to the 2nd, all over y would be my final answer to this one. So you got some maneuvering in here, and you got some fractional pieces that end up getting distributed in places. So you want to watch those and get your distributions right. Questions with this one? Again, it's using those laws of exponents that end up applying to different ones. So that was the fractional piece. So we've simplified with the fractions, but now we need to go back and clean up some simplified radical notation. So if we can simplify some of this stuff and see what happens. And these are ones that have different indexes that are involved in them. So what in the world does this mean? Well, this means I have the 4th root. This, if I turn it back into exponential format, is actually x to the 1/3. Okay with that? Okay. Then, if I turn the 4th back, it's x to the 1/3. This is our denominator. Our numerator, or our exponent, happens to be 1 when I'm dealing with this. So 1/4 times 1/3 will really give me the answer of 1/12. So that's what that one would be equivalent to, is 1/12 when I got finished breaking it apart and coming up with what my values would be. So I get 1/12 out of that one. Or if you put it back into radical form, the denominator is your index. The numerator is your exponents. They don't have anything. The x, which is your base here, becomes your radicand underneath your radical sign. So that's what that one would equate to. Okay, and you do run across these within that, and so you want to make sure that you get your combinations in there and get your stuff to come out. Okay, over here, what happens to this thing? Well, you need to break it apart because these two are being multiplied together. So I have a, what's a raised to? What would be its exponent? Exponent's 1, so I end up with 1/3. This one becomes a to the 1/2, because again, its index is 2. Its exponent's 1. My bases match, so since the bases match, laws of exponents say I can add those together. So 1/3 plus 1/2. 2 goes into 6, 3. 3 goes into 6 twice. And I get 5/6 for my answer to this one. Yes or no? What do you guys think? Not bad, I don't think. As long as you keep in mind base, the denominator of your fraction, the numerator of your fraction is always that exponent that happens to be in there. Okay? All right. One more. Let's see if we can get this one to get an answer to it. So what would I have? This is a 7, I think, in here. So turn them into fractions. So I have x to the 7/2 times x to the 2/3 all over x to the 2/5. Add. The two top ones get added. What happens to the bottom one? What would I do to it? These get added, the bottom one gets subtracted, and so you'd have to have your subtraction in there. So could I work with all these together? Yes, because I can take 7/2 plus 2/3 minus 2/5. So I could come up with their final denominator between 2, 3, and 5. And what would I end up with? 30. 5 goes into 36. 6 times 2 is 12. 3 goes into 30, 10. 2 times 10 is 20. And 2 goes into 30, 15, and that's where the fun comes. 15 times 7, 105. And then you'd add those together and add the top two. These two get added, the bottom one gets subtracted, and we end up with what our answer would be. So what would I end up with? 105 plus 20 minus 12 was 113. So my answer is x to the 113th over 30. 30th power of x to the 113th if I turn it back into exponential form. And what do we recognize from 9.2? What would happen to this? So 9.2, I'd have to simplify it. How many 30s are in 113? there's 3 of them, and so that would mean I can take x to the 3rd power out, leaving me x to the 23rd inside. So if I simplified it, that would be what my answer would be. Again, exponents, no matter how big they get, you're still looking for that pattern in here of how many groups of that you can pull out. So that's going to end up being pretty good size to work with. But it's still in there as an example of what we're doing with those. So questions with this part? Again, be careful with these pieces and make sure that you take and turn them back into their fractional form. The index is your denominator, the exponents your numerator, and the radicand, that's the bottom piece, that is your base within those. So you want to make sure that you have those. Evaluating these with your calculator, enter the value of your base, press your caret key, and we kind of went through this. Enter the fractional exponent and close in parentheses, and we talked about that too. And then just press enter, and you would have your answer to those. Now, some of them, you can end up working those things out, like these two. So what would my answer be for this first one? So if I take 125 to the 4/3 power, what would my answer come out to be? So over here on my calculator, I'm going to take 125, hit my caret key, close it in parentheses, don't forget that part. Get it back down to where it's supposed to be, hit enter, and my answer is 625. Okay, so if we work that one out, that's what our answer would be. And you do the same thing with 36 over here. So 36, caret, parenthesis, 3 divided by 5, parenthesis, get it back down, hit enter, and that one's not as easy as in a straight answer. It's 8.5, 8, 5, 8. If I round to the nearest 4 decimal places out. And a lot of times they ask you to round to 4 decimal places, so that's what that one becomes. Okay, with this one. In here, practice. Do we need to do more? What do you guys think? Are we good? Okay, because again, you're multiplying here, so you add all these exponents. This one, you're just turning it around and coming up with what your values would be, and raising it to values in there, and so forth with the other ones. More practice. Again, these are in here. If you wanted to do these, stop the tape at this point, and then you can end up working any of those out. I did go through and work them all out, and I'm going to just kind of run through this just so that it's in the video, so it's there. Not that we're going to go through and work them out, but the answers are there. And so then if I flip it and get the next page, and again, it's just having them in there to show what they work out as. And again, you can pause it at any time so that you can get an idea of what stuff is in there. And then there's another batch. And again, these are all working out the same way as what we did with them before. So make sure that you're careful and watch out what you got happening with those. So, and then the calculator one, which is putting the 100 in there and taking the 4th root of it. And then finally, just all the answers that go with that section. Okay. Any that you guys think we need to go over? Or anything with that part? Or you think you're good? Again, these have a tendency to get where they've got a lot of individual steps with them. As you go through and work on them, you might find that you're going to have to hit maybe a couple tutor buttons. Do not hop in and just do certify with this. It will not get you there, okay? You need to practice these because again, they've got a lot of different types of things to them. So make sure you do your practice. Let's take 5 minutes and then we'll work on 9.4. We'll do A and B only today. Okay, continuing with 9.4. 9.4 doesn't use the stuff basically from 9.3. 9.3 is kind of its separate little entity. It does its own little things, and it doesn't end up being used in this section for what we're going to do. In 9.4, you're kind of looking at it as the chapter from chapter 5 when we did adding and combining, adding, subtracting, multiplying, dividing polynomials. I don't know if you remember that a while back. You would look for like terms and look for like things that combine together. And that's kind of what we do with this. It's just that we've got a couple extra things in there. 9.4a, and again, it breaks this apart, and we're doing 9.4a and 9.4b today. We're going to hold off on 9.4c until Wednesday, so that you get an idea of what you're doing with some of these things. So 9.4a is performing the arithmetic operations with radicals, and this also has b in it because we get into using FOIL again. If you remember FOIL from before. First, outside, inside, last, and we're going to use that with radicals. So it gets a little complicated at some points with that, but it's not bad. But as long as you have 9.2 down, we're good to go with all of this. So first off, let's take a look at some of these things. And if you look at these first ones, they don't look like anything goes together with them at all. They look completely different and completely separate. So what we're going to look for in here is if I had the square root of 2a plus 3 the square root of 2a minus the square root of 2a, what would I come up with? Well, underneath my radical, all of my bases are identical. And this is kind of like saying if I had x plus 3x minus an x. So this radical piece is acting like that variable. And as long as they all match, and as long as they all equal each other, as long as this radical piece is identical, it's like having all x's, or having all y's, or having all z's, or having all something that matches each other. And so then what I can do is if they all match each other, then all I do is, like we did down here, we looked at the numerical part in front of these to combine them. So 1 plus 3 is 4. 4 minus 1 is 3. So I end up with 3x. The same up here. Square root of 2a, square root of 2a, square root of 2a, they all match each other. So therefore, I can take the numerical parts in front and add those together. So 1 plus 3 is 4. 4 minus 1 is 3. So this answer is 3, the square root of a squared. Now, we have to watch when we do these and make sure that the indexes all match. Because if one of these had a cube in here, let's say this one had a cube, if it had a cube, I couldn't combine it with these two because it's different, okay? This is as different as having x plus 3x minus y. It's that different, okay? If it's got a cube, these have squares, it's completely different, and I cannot stick it in there, and I cannot make it part of that problem, okay? It has to stay as itself, just as this did. If I put these together, I got 4x minus y, and that's as close as I could get to combining those, because they don't match each other, and so they're not even similar. So I have to be careful with that. So when you're combining like terms, they have to look alike. But if I go back up to my example up here, A doesn't look alike at all. If I just look at these two and say, they don't compare and they don't match, right? But if we look inside of here, there's some work that we can do in these that we did back in 9.2 because we were building on breaking this stuff apart. In 9.2, we took 32 and we either saw the common perfect square that came out, or we broke it apart. So if we take 32 and we break it to 4 times 8, 8 breaks down to 2 times 2 times 2, and 4 breaks down to 2 times 2. We know under this 32 we really have 2 to the 5th power with an x. That means the index is 2, so I can pull out 2 to the 2nd power, and leaving underneath here a 2x. We all agree? So back in 9.2, that's all we had. We just had this piece. So we had to break it apart and had to come up with what it reduced to. So kind of we're taking this and adding another step and adding another piece to it. So now we're going to do 18 the same way. And 18 breaks down to 3 squared times 2 and an x. So that means I can pull out a 3, leaving 2x underneath. This squared is 4. And now I can combine these because they look alike. 4 plus 3 is 7, the square root of 2x. And so this becomes my answer to this one. And at first, they didn't even look alike. At first, they didn't have anything in common. But when you dig a little deeper, they have some common things that are part of them. So we need to look for that, and we need to see if we can have something that matches when we get all done with these. And if there's something left in there that would make a pattern. So I took 9.2, used 9.2 to break this apart and to break this one apart. Then took those answers, combined them together because they are like. Notice again, 2x, 2x. The radicands match. The indexes match, so I can put them together. So what about this next one? What happens to 12? What does 12 break down to? So if we take 12 over here and break it to 4 times 3, 4 is 2 times 2. So 2 to the 2nd power times 3. The square root of that pulls out a 2, leaves 3. We just did 18 over here, and 18 was 3 squared times 2. Means I can pull out a 3, leaving a 2. Are we good there? Pulling out a 2, leaving a 3, or leaving a 3 outside, leaving a 2 underneath. And then what happens to 27? Well, 27 becomes 9 times 3. And 9 becomes 3 times 3 times 3. So in this one, I can pull out a 3, and it's going to leave a 3. So if I pull out a 3 and leave a 3, what happens now? So if I go back and look at this, what things can I stick together and what things do I need to leave separate in here? So if I go through and look, I've got the square root of 3, square root of 2, square root of 3. So that means this one can be combined with that one because they match. So 2 plus 3 is 5, the square root of 3. But 3, the square root of 2, has nobody to match with it, so it just comes down. Just like our y did when we combine like terms. Okay? So it's kind of taking those little mysteries and figuring out what's in there and finding some common grounds between these two and coming up with stuff that we know will come out of those. Okay? Does that make sense? So 9.2 was very important. Remember I said 9.2 follows throughout the whole chapter. So 9.2 was here. We even had a little dab of 9.2 and 9.3. So 9.2 does a pretty good job with what we happen to have. So what about this one? This one, we've got some cubes in it. So let's see if we can take anything out. What about this first piece? Anything? 5's prime, so can't do anything with 5. X is prime, so X stays. So the only thing we have with this is cube of 5x minus. But can we do anything out of this one? Same thing, pull out of it. So we're going to take 40 over here, break it down to 4 times 10. 10 breaks down to 2 times 5, and 4 breaks down to 2 times 2. So I get 1, 2, 3 2's times 5 and an x. So what can I pull out? Well, I can pull out a 2 out of here. And under that cube root leaves me 5x. So then my numerical coefficient out in front is 1 here. 1 minus 2 is a minus the cube root of 5x. Do I need a 1 in front of it? If you put a 1 there, Hawks is probably going to complain. So don't put a 1 here, just put minus. Don't forget your subtraction and watch for that part. Okay, so what about D? See what you guys can do with it. Again, it's breaking it apart like we did in 9-2. So you want to break your pieces apart, find out what combines together. Now when you check this thing, these also, the letters out in front and then the letter portions have to match as well. So notice it's x and y, and under the radicals a y, so they match each other. So then only thing that needs to be combined is the numerical coefficient piece. So 2 minus 5x, y, the square root of y, is 3xy, the square root of y, would be your answer. So you're pulling out stuff that can match in there. I didn't rewrite this one because a squared means an x pulls out. A cube means I can pull out a y and leave a y. And so we end up getting that for our final answer to that. Hopefully you got that when you work that out. Okay. How about this one? See what we can get with this thing. Can I, whoops, I get the whole problem up there, wouldn't it? Can I take anything out of there? Does the sixes break down? 6 is 2 times 3, so not much happening there. So what would my final answer be on this thing? The radicands are all 6s, so that matches. The indexes are 2 and 2 and 3. So as soon as I say a 3, I know that's different. So that's like having a y here. So it doesn't match. So only things I can put together are these two. -8 and -3. -11, the square root of 6, plus 7, the cube root of 6. So I can't bring that piece down and do anything else to it. Okay? So thoughts on these? Do you do another one? Are you good? Again, it's 9-2. Separate pieces are all 9-2, and seeing if you can break stuff apart and come up with those. Another one? Are you okay? What do you guys do? One more? Yep, we can do one more. Let me get my notes over here. I can pull up another one. We'll do this one. How about the cube root of 40x plus 3, the cube root of 5x, minus 2, the cube root of 135x. So again, breaking them apart. So you get your 9x stuff in there so that we get or the x stuff, and breaking the 40 apart and breaking 135 apart to see if we can get anything out of those. So that's what happens with this one.
The one that you planned on
This one,
yeah, when the very bottom.
right here.
Yeah,
Where did this 3 go?
underneath that.
Oh, here? This is the final answer.
Oh, okay.
Okay, that's the final answer. Because I took 2 plus 3 is 5. 5 from a -6 is a -1. Okay? Yeah. No, that was the final answer. Did you get that for a final answer?
I was watching you work it out.
Okay.
And then
Okay.
you want to work it out.
Yep. Yep. But you want to, I ended up taking 40 over here on the side, breaking it apart. Took 135, broke it apart. Got my prime factorizations in here so I could see what I could pull out. This way, because it's a match, I can pull a 2 out. The 5 and the x stay. This one, there wasn't anything done to it, so it just comes down. This one, the 3 could be pulled out, but I wanted to show you that 3, and it was 2 times this, so 2 times 3 gave me the 6, and the cube root of 5x just came along. Then all of these match. So that means the numerical parts, excuse me, I can combine and put those all together and end up with this for my answer. So that's what happens to it. Okay? That makes sense then? Does that help? One more? Okay. One more. Just pieces. Remember, it's a piece, it's a piece, it's a piece. We did pieces when we did chapter 7, and you had to factor each section apart. So that's the thing with these, is when you look at them, see what you can do with each separate piece. Okay? So each separate piece is going to break apart, and you'll come up with what your values happen to be on those. The last section piece that we're going to do is multiplication of radicals. And with the multiplication of radicals, any time that you take two identical radical pieces and multiply them together, the square root of 5 times the square root of 5, you are only going to end up with straight 5, okay? The reason is this is 5 to the 1/2 times 5 to the 1/2. In our exponent laws say add a half together. 1/2 plus 1/2 is 5 to the first power, or simply 5. So it's key to understand that piece is that every time I've got a matching root and the radicand underneath matches and the root matches, if it's a square root, we can just drop the square root. Now be careful with cubes and fourth roots because they don't drop that same way. So this only works with square roots. So it only works with square roots. So we want to be able to drop that piece and end up coming up with what it would be. Okay? So if we can drop it, then we're good to go. So a square root of 5 times the square root of 5 will equal the radicand that's underneath it. A square root of 2 times the square root of 2 will equal 2. Okay? Square root of 7 times the square root of 7 will equal 7. So if you keep that in mind when you're doing some of these, it does help with your multiplications because then you can just end up removing those. So if we go back up to this piece, what does this mean? Well, one way of looking at this is the square roots are the same. So what we do is we multiply the radicands underneath. So 5 times 15. Now, before I do any of the multiplication in here and take 5 times 15 and put it on my calculator and come up with 75, I don't want to have to do that because if I can break 15 apart, and 15 is 5 times 3, and I get 2 5s, what can I do with those? I can pull them out, right? So this answer is really 5 the square root of 3 because these 2 5s can be removed from underneath there. So before you hop in and get 75 under here, then have to break 75 apart and get 3 times 5 times 5, there's no sense in doing this extra step. Break your pieces apart right here so that you can see what parts you have in there. So don't hop in and do your multiplications first. Break them apart when they're smaller so then you can see what can come out of those. So I can pull 2 5s out and I end up with 5 the square root of 3. So what happens to this next one? Well, the next one is kind of, it's a distribution. So I'm going to multiply the square root of 7 times each piece in here. So square root of 7 times square root of 7 will give me 7 because those are the same values, minus the square root of 7 times square root of 14 is really 7 times 14, or 7 times 2 times 7. So I can pull out a 7 and be left with the square root of 2. So in breaking these apart, don't hop in and do that multiplication because if I took 7 times 14, I get a big number, right? And that big number, then I need to break it apart. It's easier to just break 14 apart and come up with 2 times 7 instead of taking and ending up with, what do we get, 98. Instead of taking 98 and breaking 98 apart and coming up back with the exact same thing we have here, you might as well just break 14 apart and see what you can pull out. And so you're looking for those common things in there. So this distribution, again, a square root times a square root of the radicands are the same. You can just drop the square root sign. So you can get rid of that piece. Again, that's only with square roots, not with the other roots. Sometimes we have to find out what those other roots would end up being when we work through those. Do we need to do another one like this one? Or you think you're okay? This times this and this times this. Think you're okay? Okay, because we can do some more. In fact, probably what I'll do is pick out some more because I'm kind of a little bit skimpy on my note stuff that's in here. So this one is straight foiling. So foiling, F stands for first terms. O is outside terms. I is for inside terms. And L is for last terms. And we do this, and you did this where you've had x plus 4 times 3x minus 7. And you did x times 3x is 3x squared. X times a negative 7 is negative 7x. 4 times 3x is 12x. And 4 times a negative 7 is a negative 28. Then we take our middles and combine them and get 3x squared plus 5x minus 28, and that becomes our answer. So when we do general run-of-the-mill foiling, we're just, again, multiplying first terms, outside terms, inside terms, and then finally the last terms. When you get into radicals, they are pretty much the same. It's just that we have to be careful with what we end up with and what we multiply together. So when I do this first piece, first term times first term, and I get that multiplication, what do I get out of it? Well, I get 3, the square root of 7 times the square root of 7, ends up leaving me with 3 times what? Square root of 7 times the square root of 7 is just plain old 7, right? So we got that piece. Square or 3, the square root of 7 times a positive 3. The only piece that multiplies is the 3 times 3, and I get 9, the square root of 7. We good there? Second part, I multiply these 2 together. I get negative 2, the square root of 7. And then finally the last, negative 2 times a positive 3 is a negative 6. And I'm not done because I got to do some multiplication here and get 21. 9 and a negative 2 is a 7, the square root of 7, minus 6. And in most cases, the first term and the last term will now combine in these. So 21 and a negative 6 leaves me with 15. And so instead of having 3 terms like I had over here, I'm down to only 2 terms when I put that together. Okay? So again, foiling, making sure I multiply stuff together. And if these didn't match in here, then I would have to multiply the stuff that's inside. Okay? So that we can end up seeing what happens with that. Questions on this one? But we'll do a few more so you get an idea of what we need to do with these. This one, since it's got a square out here, that means I need to see this whole thing twice, right? So I'm going to take the square root of 6 plus the square root of 2 times the square root of 6 plus the square root of 2. And if I FOIL this, square root of 6 times square root of 6, what happens? 6. Square root of 6 times square root of 2 is going to be the square root of 12. And we're going to leave it sit there for right now, because all we're doing is just the foiling piece. And then if we got to come back and adjust stuff, we will. 2 times 6 in this case. All we do is multiply the radicands together and I get the square root of 12. And last, square root of 2 times square root of 2 is 2. But the square root of 12 can be reduced because I can pull a 2 out, leaving a 3. Then I'm going to use my rules from 9.4a and combine stuff. So 6 plus 2 is 8. 2 to the square root of 3 and 2 to the square root of 3 is 4 square root of 3. Now you could have put these together right at this point and said you had 6 plus 2, the square root of 12 plus 2, and then adjusted your 12. So it would work either way. So you could adjust it at the end if you wanted to, or adjust it at the other point. Okay? Make sense? Okay. Let's go to this guy and see what happens with that one. So again, the reason we multiplied 6 and the 2 is because they did not match each other. So we multiplied the stuff underneath there. So what happens with this one? Square root of 2x times the square root of 2x is 2x. Square root of 2x times the negative 5 is negative 5, the square root of 2x. Negative 5 times square root of 2x is another negative 5 square root of 2x. And last, negative 5 times a negative 5 is a plus 25. And then we need to see if we can put stuff together. So 2x doesn't go with anybody. Negative 5 and a negative 5 is a negative 10, square root of 2x. And 25 doesn't go with anybody. So it comes down there, and it's part of that answer. Okay. Yes? No? Here's another one. What happens with this one? Square root of 3x minus 4 times the square root of 3x plus 4. See what you end up with. So you should end up with 3x minus 16 if you did everything right. You guys get that? Square root of 3x times square root of 3x is plain 3x, because we can drop it because the indexes are the same. Times 4 is 4 to the square root of 3x. Negative 4 times the square root of 3x. And finally, a negative 4 times a positive 4 is a negative 16. Middle terms cancel each other out, so they're no longer there. So we got rid of all the radicals. We're going to use this type of a thing in 9.4c to get rid of denominators, but that's not today. That's next time. Here's another one. What happens with this one? 2, the square root of 2, get over here where you can see, minus the square root of 7 times 2, the square root of 2, plus 5, the square root of 7. This one, be real careful because you got to multiply 2 times 2 first. You get 4. Square root of 2 times the square root of 2 is 2. So you got an extra multiplication here in this one first spot. So you get 8 out of that. Then when you multiply 2 times 5, you get 10. The radicands do not match, so 2 times 7 is 14. Then negative 1 times 2, and 7 times 2 gives you 14. And then last, negative 1 times 5 is 5. Square root of 7 times square root of 7 is 7. So you get your combinations in here. 10 minus 2 is 8. Then your 8 from 35 gives you 8, the square root of 14 minus 27. Okay? Be really careful with your multiplications. Take the time to write your steps down. Don't try to do it in your head, okay? Because that'll be, again, a number one spot you can make mistakes is because you don't remember what you've written. So make sure that you go through and do each one of these on paper and take it down so you're writing out everything. Even if you have to write it out even more than what I have here and write out each piece separately, do that so that you get that combinations together of what you got to do with those. Do we need another one of these? Are you okay? You guys think? Need another one? Are you good? Okay. Again, you might need to use your tutor stuff. Do not, again, on this one, hop in and do Certify. You might think, oh yeah, I can just go to Certify with it because it's just combining like terms. But there's some little things in there that can throw you off. Okay. So make sure you do your practice with that. And then Certify, if you get kicked out of Certify twice, you got to go back and do practice anyway. So because it won't let you in Certify. So you haven't gained anything really. Where if you sit down and do a good practice, then go to Certify, you're really saving yourself less time than jumping into Certify and failing it twice and then having to go back to practice. So you're defeating your purpose in there. So make sure you do that. So I'm going to turn this thing off.